Welcome to lecture this morning. We're going to be continuing to look at classification today and finishing up our module on machine learning this week. So some announcements. Next week, all office hours, discussion, lab, tutoring sections, all canceled next week. We will have lecture on Monday. The final exam, as I mentioned last time, is going to be in person. So we have a default in-person exam. There's a post on Ed describing all the details. If there's a problem with you attending in person, like if you're not here in Berkeley, we will have an online alternate exam. And if you need the online alternate exam, please go read the Ed post and fill out the form by this Sunday, 2 days from now. We'll have our last homework coming up, released today, due the last week of classes. Don't forget your Project 3 checkpoint is due today. If you haven't already submitted, please finish up to the checkpoint and submit today. And then the final project will be due the last week of classes. Okay. So we've been looking at classification and diving into how to build a classifier using nearest neighbors. And I was in the midst of showing you how to implement this in Python on Wednesday. And so today I'm going to continue where I was with implementing this classifier in Python code. Hopefully this will be useful for your Project 3. And then I'm going to look today at how we evaluate the accuracy of a classifier. How good is the classifier we built in this way? So as a reminder, we're looking at nearest neighbor classification, which predicts the label of some example, like some patient, by finding the nearest neighbors, the most similar data points from some historical data set. A historical data set is called the training set. And then we predict the class of this new example by using a majority vote of all the neighbors, of all the nearest neighbors of this example. Okay, so a little bit of a refresher here and a reminder. The procedure we're using to find the k nearest neighbors of an example, we walked through some code for this last time, was we found the distance between the example and each data point in the training set. We added a column with those distances. We sorted the training set by distance. And then the nearest neighbors rose to the top, and we took the top k rows of this sorted table, and that was the k nearest neighbors. So we built code to do that on Wednesday, and that's what we're going to be working from. And now to get a nearest neighbor classifier, we're going to use that code to find the k nearest neighbors of the example. Then we're going to look at the classes of those neighbors and take a majority vote. See which class is the most common among the nearest neighbors, and that will be the prediction that we make. Okay, so I wanted to walk you through how you implement this in Python. So we had this data set here of historical patients who had this this breast cancer test done, and we built a function to compute the distance between two rows in this table, and we built a function that would compute a table with all the distances added, compute the distance to each example in the training set, and we built a function that would sort those by distance. And so, for instance, if we took an example, one patient with some particular test results, then maybe I could show it a little bit better way this way. took one patient with some test results. Then we went and in this case, I said, well, let's suppose the training set was everything other than this one patient. Then we found the 5 nearest neighbors to this patient in that training set. And here they were, and here's the distances to each of those. So what prediction would I make for this example, given that these are the 5 nearest neighbors? What class would you predict? 1, because 1 is the majority, 1 is the most common. You can see there's 4 votes for 1 and 1 vote for 0. So class 1 wins. Okay, good. So we're going to write code to do that now. Write code to do that majority vote. So what we really care about now is this in these 5 nearest neighbors. The only thing that really matters is the class column. Everything else is irrelevant. So we need to figure out which number is more common in this class column. What kind of a table operation might help us figure out how many 1s and how many 0s there are? Group will help us figure out how many 1s there are and how many 0s there are. So we can write some code to group by class. And let me just show you what happens if you do that. I group by class, and you can see here it says class 0 has 1 vote and class 1 has 4 votes. And now I want to know which has the most votes. And so there's a handy thing I can do is if I sort by count, then that brings the most common class to the top. So now there it is, sorted by count. And then how would I get the majority class? Yeah, I want the first row in the class column. So I could take out the class column and then dot item 0 of that. Okay. So let's give this a name, and then I could do class dot item 0. Right. And there it is. Majority class is 1. So don't I have to sort by count? Yes, I do have to sort by count. Descending equals true first. And you can see right here, I did the sort operation. So I grouped and then I sorted. And that was why the one with the largest count went to the top. And once I've done that, see here is the sorted table, then I can get the 1 at the top. All right, so let's put this in a function to do this for any data set. And this function is going to take this table with the k nearest neighbors, and then it's just going to do this code that we did, that we just wrote just now. And that is now a function that will compute the majority class among all of the k nearest neighbors. And finally, we're ready to write the classifier. Remember the classifier, we find the k nearest neighbors and then take a majority vote. Well, on Wednesday, we wrote code to find the k nearest neighbors. Right now, we wrote code to take the majority vote. So we just have to piece those two together. And it's actually very easy. We take this function that we wrote to find the k nearest neighbors, and then we run that, and then we pass the result of that as an argument to this majority class function we just wrote that takes the majority vote among them. Okay, so this code is going to find the k nearest neighbors and then take the majority vote among them. All right, so we get a function now, classify, that we could use with any data set, and it has 3 arguments. The first is the training set. The second is the specific example or data point or patient that we want to make a prediction for. And then finally, we have to tell it what value of k we want to use, how many nearest neighbors to look at. So if we take an example here, we said we had a single example of a single patient. With some attributes, and we had a training set, and we're going to now classify. So we call the function like this. And this makes a prediction that says the 5 nearest neighbors for this patient had a majority class of 1. So we're predicting 1. We're predicting malignant for this patient. So let's now compare to see what the actual class of this patient was. The actual class of this patient was 1. So was the classifier's prediction correct for this patient? Yeah, we predicted 1, the truth was 1. So in this case, the classifier happened to be correct. Now, it won't necessarily be correct for everyone or all the time, but it was in this example. I don't know. Here's another example. We'll take a new example of a new patient. This patient looks like this. We said, suppose I used as my training set everything other than that patient index 10. What class would I predict? This code said predict class 0. And now let's take a look at their actual class. Class 0, also correct. Why am I doing this exclude? I see his function in the chat. That is a great question. Why do I do this exclude? Maybe I shouldn't do that. What would happen if I left out the exclude? That seems like a reasonable thing to do, right? Oops, there's a problem here. If I used all of the patients in this data set as my historical data, and I picked patient index 10 as my example, I'm comparing patient index 10 to everybody in the training set, including itself. What's the distance when I compare patient 10 to itself? Distance 0. Yeah. So that's going to be the smallest distance, the nearest neighbor. And if I had used k equals 1, I would be making a prediction based on that patient's own class, which is known, but it's kind of cheating, right? It's kind of cheating because in real life, you're not actually going to have the specific patient you want to make a diagnosis for in the training set. You're going to have some past patients. So I'm kind of doing a little bit of a simulation here. What I really want to simulate is if a new patient arrives, and then I want to make a classification for that new patient based on the past patients. That new patient's not going to be in the training set in that real world situation. But I don't have a new data set of a new patient showing up with a known class that I can sample from. All I have is the data I was given. So what I'm doing is I'm picking out one of the patients from that data set and say, let's pretend they're the one who showed up today and everyone else are the historical data who came before. Does that make sense? So if I didn't exclude, I would be like cheating. Yeah, thank you for asking that question. That was a great one. I really appreciate that. Is this classifier function only using 2 attributes? Nope, it's using all the attributes. We wrote code to compute a distance that works with any number of attributes in any number of dimensions. And it does the differences between the attributes and squares them up and adds them up and works for any number of attributes. How do we decide what K is best? We're going to get to that. We're going to get to that. Basically, it's trial and error and see what happens, what seems like it's working the best. Okay. Brief pause here. It's raining. I need to run inside. Give me just a moment.
I am so happy we gave ourselves an extra lecture for this. In the future, we're going to have to count on running in for the rain. This is wonderful. This doesn't happen when you're lecturing in Wheeler Road. This is great.
Yay, my plants are getting watered. All right, brief break. All right. One last example. Here's another patient. I'm imagining patient index 15 is the new one. You can see made a prediction was 0. And in this case, the prediction was wrong. So this highlights that our classifier is not going to be perfect. It's our best guess, but some may be inaccurate. Okay, so just a reminder, what we did, we computed the distance from this example to everything else in the training set. We found the k nearest ones, like maybe 5 nearest ones. We took a majority vote of their classes, and that was our prediction for this new example. So you've now written the complete code of a machine learning classifier, which is pretty amazing that you can do that in a first class on this topic, I think. Okay, let me pause for questions. Should k always be odd? Yeah, you might notice that I am always using an odd value of k in this class. And you got it exactly right. If I used k of 4, if I found the 4 nearest neighbors, what would I do if half of them said class 0 and the other half said class 1? Now it's an even split. It's a tie vote. How do I make a prediction? That's kind of annoying. And so what I'm just going to do is if I pick an odd value of k, I don't have to think about it. I mean, there are things you could do. You could like say, if it's a 50-50 split, always predict 0. Or you could say if the 50-50 split, just flip a coin. But we're going to have to make some prediction. So it's kind of handy that we have an odd k. So there will always be a winner, a majority winner. This is to test an AI. We're building an AI in some sense. I mean, as you can see, it's not actually very intelligent. It's just looking for patterns and similarities in the data. Okay, so now let's say I built this classifier and I go to a doctor. I go down to my nearest Kaiser office and I say, doctor, I did it. I've got this classifier that will analyze these lab test results and make a prediction whether the patient has a malignant tumor or not. The doctor says, okay, what's the catch? And I say, well, it's not perfect. It makes the best guess. And but it's most maybe, it may be right a lot of the time, but not always. And then what's the doctor going to say? They're probably one of the first questions they're asking is, well, how often is it wrong? How good is this thing? How often is it right? And how often is it wrong? I better be prepared to answer that. I better have a way to answer that. Okay, so to do that, we're going to measure the accuracy of the classifier. The accuracy of a classifier on some data set is the proportion of examples where the prediction of the classifier is correct. All right, so this is a number that indicates how good your classifier is. Like if you have 50% accuracy, this is no better than flipping a coin. If you have 80% accuracy, that's better. If you have 99 accuracy, wow, that's great. It means it's only wrong 1% of the time. If you have 100% accuracy, it's perfect. It's always making the correct diagnosis. Okay, so we better have a way to measure the accuracy of a classifier. So how are we going to do that? We're going to need to compare the classifier's predictions to the correct answer, right? So this is like writing an exam. If I'm going to give you an exam question, I better give you one that I know what the right answer is. So I'd compare whether you got the right answer. So when we test the classifier, the natural way is to test it on some data, but we better make sure it's data where we know what the right answer is. So we're going to need a data set where we know what the class of those patients are. So that's what we do, is we arrange for a data set of patients where it's known whether their tumor was malignant or benign. We run the classifier on each of those patients, and we compute what proportion of times it got, the prediction it made matches what we know is the correct answer. Okay, so that's how we evaluate accuracy. We call that data set of patients the test set. We're testing the accuracy. if the test set, the patients in the test set are sampled at random from the entire population of patients, then we know by the properties of a random sample that the proportion that's correct on the test set is a good estimate of the proportion on the entire population where it's accurate. Okay. So if I got 80% accuracy on the test set, then that makes me say, okay, I'm going to estimate it's probably about 80% accurate on the entire population. And of course, accuracy on the population is what we ultimately care about. Okay. So this is how we evaluate the accuracy of a classifier: is we get a test set that's sampled at random from the population where we know the correct class, and then we compute the proportion that's correct on the test set. Can you use confidence intervals for classifiers? Absolutely. You could totally use your confidence interval stuff. So if I had my test set was a random sample of 100 patients, and my classifier was 80% accurate on that test set, then you could figure out a confidence interval for what the accuracy on the population is. Could be a little bit higher than 80% or a little bit lower, but not too much higher, too much lower. And the confidence interval would let you compute what range there is a 95% confident range. Would this work if I didn't know the class but had other information? No. You have to know the class of everything in the test set, because you have to be able to tell whether the classifier's prediction was correct or not. So when the classifier makes a prediction for that patient, it says, I think that's malignant, I have to have a way to know whether the classifier was right or wrong. So I have to know the true class, the correct class for that patient. So where do we get this test set from? I've got a data set of historical data from my patients this training set that I was using to build up a classifier. Can I use that data as my test set? No. Why not? I mean, that was randomly sampled from the population, so I'm good, right? Cheating, total cheat. What would happen if I took my training set of 500 patients and I built a nearest neighbor classifier with that, and then I use those same 500 patients as my test set? I would be 100% accurate on the test set if I used a k=1 nearest neighbor classifier, because for each patient, remember, it's the situation with the exclude we were talking about. For each patient in the test set, I'll be finding the nearest one in the training set, but that's itself. That's itself. And so I'd be looking at the correct class and making a prediction based on the correct class, and that would be the correct prediction. And so the nearest neighbor classifier would be correct. So I would get 100% accuracy on the test set, and yet this classifier might be terrible on the proportion on the population, or it might be great on the population. I can't tell. I have no way of knowing. Yeah. So if you want an analogy, this would be kind of like if I gave you the sample final exam from last semester and I said, hey, study this. This would be a really good one to learn from. Go make sure you know how to solve all the problems on this final exam from last semester. And then the final exam for this semester was an exact copy of that practice exam you were studying on. You could get the right answer every time by just memorizing what the answers from the practice exam were without knowing anything about data science. It wouldn't be a good test of your knowledge of data science. So we need the test set to be separate from the training set. So typically what we do is we use what's called a holdout procedure. We get a data set of patients with a known class, and some of those we're going to use as the training set, and some we're going to use as the test set. So we might randomly shuffle them and then take some fraction of those, call those the training set. That's what we're going to build the model from. And then the remainder we're going to save and set aside. That's called the test set. And we're going to use that for evaluation of accuracy. And we put that aside and we don't peek at that. We don't look. We do all our work to build up a classifier, the best classifier we can. And then once we're done, we take the test set and we measure the accuracy of our classifier on the test set. Okay. So both the training set and the test set require labeled data where we know the correct label, the correct diagnosis. So this is where we take a big data set and we split it into the training and the test set. So let's see. Oh, all this workup about how to compute the accuracy of a classifier. Now I'm dying to know this nearest neighbor classifier we just built for diagnosing breast cancer, malignant versus benign. Let's see how well it does. So we have patients here. We have 683 patients, and I'm going to separate out this data set into half of them for a training set and half for a test set. It'd probably be more common in practice to take like maybe 80% for the training set and 20% for the test set, but it's not too critical. So what I've done is I've randomly shuffled this data set and taken half of it for the training and half for the test set. Why did I randomly shuffle? Does it matter? It's just kind of a detail, but just in case, I don't know where this data set came from. Maybe the researcher helpfully organized it. So they put all the people benign patients first and all the malignant patients last or something like that. And then it wouldn't be a random sample. So randomly shuffling should allow this to make this a random sample. Okay. So now to evaluate accuracy of this classifier, what I'm going to do is I'm going to classify using the training set each example in the test set. So I am iterating over the entire test set here. And for each in the test set, I'm classifying it. And then I'm testing whether the prediction from the classifier matches the true class and counting that and returning that proportion. All right, so don't worry too much about that code. It's just doing what we talked about. So now for the big reveal, let's take k nearest neighbor classification with k equals 5 and evaluate the accuracy of the classifier we just built on this data set. Remember, Brittany Wenger got 99%. So let's see what we got. All right, 96.7%. Pretty sweet. Pretty sweet. Not bad, right? For us with no medical knowledge of what the meaning of any of these attributes are, that's remarkably good. All right, so people were asking, how do you figure out what the best value of k is? And basically it's trial and error. So let's try a different value of k. Maybe we could try a smaller value, k equals 3. Or maybe we could try a bigger one, k equals 11. This is going to take a while. Why is it going to take so long? Because what we're doing is for each of the 300 things in the test set, we're comparing it to all 300 in the training set, and we're computing a distance and doing some complicated stuff. So we're comparing each test patient to hundreds of things in the training set, and then we're doing that itself hundreds of times. So there's a whole lot of work happening here. All right, so with k equals 3, you can see, about the same, maybe tiny bit lower, but basically the same accuracy. With k equals 11, I made a bigger k, and it looks like it might have gotten a little bit better, maybe a little better, a little bit up to 97%. With k equals 1, it was a little worse. It was below 96%. So it's not making a huge bit of difference in some sense, but here we're at the range where every little bit helps. If you said, do you want something with an error rate of 3.4% or 2.7%, that, I'd take the 2.7%. Every little bit helps. So this is how you would choose a value for k, is you try different values for k and see which seems to work best on your data set. Okay, so we're doing pretty good. Now, Brittany was using a more sophisticated technique. She did, it was a lot more complex and she had to do a lot more work. You can see how it takes some work to get even a 0.5% improvement on accuracy. She did a lot of work and she managed to get it up to 99%. And she used more sophisticated techniques, neural networks you can learn about in later classes. Another technique she had was she built a classifier that on some examples, they could figure out how confident it was on each prediction. And on some examples, it would just say, I don't know. So it's rare that, as Professor Adhikari says, it's rare that you can achieve 100% accuracy in machine learning. decisions. Here, we just don't have all the information. And so there's almost always some chance, some possibility of being wrong. Okay, so this is how you evaluate the accuracy of a classifier. So let's talk a little bit about some general comments about how to build effective machine learning classifiers. Some caveats. One caveat is that the effectiveness of machine learning classifiers is very dependent on the data that you have for the training set, the data that you have to learn from. And today's classifiers typically require a lot of data. And I wanted to show you one example, maybe give you some intuition for why and what can go wrong with a machine learning classifier. So let's imagine that we have a machine learning classifier that is trying to classify an image to tell whether that's an image of a dog or an image of a wolf. Pretty challenging task. Here, maybe the attributes are the for each pixel, the color of that pixel. Okay, so you can build classifiers to try to solve this task, and we could take a training set. Let's say we had a training set of images like that shown on the left, of pictures of dogs and pictures of wolves, and train a classifier, teach a classifier to predict which of those are dogs and which are wolves. Suppose that you built this classifier and you have an image in the test set that looks like on the right. That's a dog, right? Let me tell you something that can happen. That can get predicted as a wolf. In fact, with many existing machine learning classifiers, it's very likely that will get classified as a wolf. Does anyone have any ideas why? The snow, the background. It's really easy for a machine learning classifier to look at the background. And these pictures of dogs typically are on a colorful background. And the pictures of wolves are typically on a white background in the snow. And telling a dog from a wolf is really challenging. But telling white from colorful is much easier. There's a very strong correlation here in this training set between background and the correct class. So there's a very good chance the machine learning classifier would learn to pick up on the background, white versus colorful. And if it's a mostly white image, say wolf, and if it's a colorful image, say dog. So now when you've got a picture of a dog on snow, it's mostly white, and your classifier will predict wrongly. It'll think because of the snow that it's a wolf, but it's actually not. What could you do about this problem? Say you ran into this in practice. Any ideas for what you might do? You're not happy about this. Somehow get the classifier to ignore the background. Okay, maybe we could do some pre-processing of the image to figure out what's background and what's not, and like blot out background. That might be a little challenging. It turns out figuring out what's background and what's not is a non-trivial image processing task to do automatically. Different attributes, maybe if there's some other attributes other than just the image. Okay. Add more photos to your data set with different backgrounds. Yes, that's another good idea. That's a really good idea. So another possibility is to get more data in the training set that's representative of the full diversity of things that might happen. See, our training set here was not fully representative because sometimes dogs are on snow and sometimes wolves are running around on grass. So that's another reasonable approach, is to go look for more data that covers the diversity of what can happen in real life. And in fact, this is a common method that people often use in practice, is they go look for either make the training set very large, get a very large data set, so it's likely to cover these less common cases of dog on snow, or they go deliberately look for images or data points that are likely to contain these unlikely cases. They go out and they send a photographer and say, hey, would you take a picture for me of a dog on snow? And, you know, they go searching for images of wolves on grass and so on. Good, good. Okay, so yes, multiple reasonable approaches. In practice, often when our classifier is wrong, we don't know why it's wrong. In this example, I could tell you a story about why it's wrong, but it may be very hard to tell why it's wrong. So it may be very challenging to make an intervention that works by removing some of the attributes. Yeah, so gathering more data is often easier. But all your suggestions here are really good ones, really good ones. You could remove the background if you knew this was the issue. Okay, so this illustrates one reason when you may have heard people talk about big data. Why is industry, why are companies so obsessed with big data, with gathering? Why do they want to gather lots of data about your behavior on the web? Why do they want to gather data about lots of people? It's because these machine learning algorithms work better when they have more data for the training set. It can help them avoid these spurious confounding combinations. It just works better. And so there's a lot of incentive for them to gather a lot of data, because then they can build better machine learning classifiers. Random question. When you have the I'm not a robot test, where you're asked to indicate which images, which images have traffic lights. What's happening there is a brilliant idea. That's a brilliant idea that came out of some research. Some of those images are ones where they know whether it has a traffic light or not. And so they're testing you to see whether you answered that correctly, whether you're a human or not. So perfectly reasonable way to test whether you're human or not, because it's challenging for a bot to tell which images have traffic lights and which don't. But humans can easily pick out which ones have traffic lights. But they've snuck a few in there that they don't know the answer to. So maybe 10 of them, they know the answer, and 3 of them, they don't know whether they have traffic lights or not. And so you're answering, and if you're a human, then you have just indicated they learned from you whether those 3 actually have traffic lights or not, so they can add those to their training set. So that test is a combination of 2 things. One, testing whether you're human or bot, and then sort of for free, while they're doing that, they're gathering a few more labels on some images so they can add to their training set, so they can try to build a better classifier of which images have traffic lights, maybe so for their self-driving cars or something like that. All right, that's it. That's an aside. You don't need to know that for this class. Isn't that clever? Free labor, totally. All right. So when you're building a machine learning classifier, you want to make sure that your training and test sets accurately represent the population in which your classifier. You can get into trouble if your test set does not accurately reflect the population of data that you're going to be using it on. For instance, if I have a test set that was gathered of only male patients, and then I go use this classifier on both men and women, who knows how well it's going to behave on the women. My test set didn't reflect the full population. Another thing that can go wrong with machine learning is what's called overfitting. And overfitting is when a classifier does really well in the training set, but doesn't do as well on the test set. There are multiple reasons why this could happen. One is if the test set's not reflective of the training set, or the test set are not reflective of the population, that can cause overfitting. Another way it can happen is if the classifier just didn't learn very well. So for instance, if I gave you a practice exam, and then the final exam was the same as your practice exam, as I mentioned, you could get a perfect score on the final exam just by memorizing without having actually learned anything about data science. And so if the classifier is just memorizing what to do on the training set and hasn't learned any more general patterns or general ways to decide for other images that weren't in the training set, then it might do very well in the training set and perform poorly on the test set. And you can learn about ways to deal with that problem if you take further machine learning classes. The most basic ways are make sure the training and test set are reflective of the population and get more data in your training set. Let me mention one more technique that is very helpful if you're working with nearest neighbor classifiers. When you're using a nearest neighbor classifier, the nearest neighbor classifier is based on similarity between data points. And we're using the distance between two data points as our similarity, as our measure of similarity. So let's look at this chronic kidney disease data set. Take a look at these attributes. You can see the glucose ranges, maybe a few hundred. The hemoglobin ranges typically are around, 5 to 12 or something like that. And the white blood cell count numbers vary from 1,000 to 10,000. Suppose I have a new test point and I'm computing the distance to things in this data set. Which attribute do you think will have the biggest influence on the distance measure? The white blood cell count. Yeah. If I have a new patient that's just like the first row in this table, but maybe has a 10% higher value for everything, 10% higher for hemoglobin is going to be only about like 1 higher. So it's only going to add like 1 to the distance. But 10% higher in the white blood cell count is like 600 or 700 higher. So it's going to add like 700 to the distance. So the distance is going to be dominated by differences in the white blood cell count column. Okay, so small relative distances to white blood cell count will turn out to make a very large contribution to the overall distance. And that has the potential to swamp any differences in the hemoglobin. If I had a patient whose hemoglobin was 20, by relative measure, that's a humongously large hemoglobin, but that's only a difference of 10. So a distance measure set is not very much compared to the differences that are happening from the white blood cell count. And it'll just get overwhelmed and dominated by what's happening in the white blood cell count attribute. So if you were to use nearest neighbor classification with this chronic kidney disease data set using the techniques I showed you, it turns out it wouldn't work very well. And you might not know why, but the answer why is because it's effectively as though it's pretty much only looking at the white blood cell count attribute, and the other attributes basically don't count, which is not an effective use of the data. We would like a classifier that's making good use of all the information that could help us make a prediction. So how are we going to fix that? It's right there in the title of the slide, and it's there in the chat. If we convert these to standard units, then a 10% relative difference will be about the same absolute difference for all columns. So it's often, when you're using a nearest neighbor classifier, often very helpful to standardize the data, convert to standard units. Question in the chat: could you instead weight each variable? Maybe certain variables matter less than others. Yes, in this example, as you look at this, you could see that there's a lot more variability in the white blood cell count than in the hemoglobin. So you could, instead of, when you're computing the distance, instead of summing the squares of the differences, You could weight this difference, downweight it. Or you could upweight this, maybe multiply the difference in hemoglobin by like 100 or something like that to try to put them on the same scale. But if I want to do that, I have to figure out how much should that weight be? How much larger should I make it so that these are going to have about equal influence? And a good way to figure out what those weights should be is they should be proportional or inversely proportional to the variability in that column. And how do you measure the variability in a column? By the standard deviation. So here, the standard deviation might be something like 100 times higher than it is here. So it would be reasonable to multiply the hemoglobin by something like 100, whatever that ratio in their standard deviations is. And if you think about what converting to standard units does, that's exactly what it does. It's like multiplying by a weight that is proportional to the standard deviation. Well, 1 divided by the standard deviation. Okay, so your idea of weighting each variable is a very good one. You need a way to come up with the weights, and converting to standard units is a way to come up with weights that is principled and will work well. Okay, so let's see this in action. We have this previous data set of chronic kidney disease patients. And let's build a nearest neighbor classifier on this data set. So I have the basic data set, CKD, which is the data set we were looking at before. And I'm also going to build a version of this where I've converted each column to standard units. And so when I convert to standard units, it looks like this. Now the attributes are in standard units. Okay, so I've got 2 versions of this data set, the original and the standardized. So let's build a classifier. We have all the code that's needed for this. I have to take this data set and split into a training set and a test set. So I'm going to randomly shuffle the data set, take the first half of them as my training set and the last half as my test set. And then I'm going to use nearest neighbor classification. And I've just arbitrarily picked k equals 3. This was not something that was carefully chosen. I just pulled a number out of thin air. And I'm going to evaluate how accurate the classifier is if I use standardized data set and standard units. And you can see here that using all of these attributes, nearest neighbor classifier with the standard units data set is able to get over 98% accurate. So that's really good. Now let's compare what you get if you did not convert to standard units and use the original data set. Everything else the same, just not using standard units. Now you can see the accuracy is only 80%. So 80 versus 98%. And the reason for that is exactly this problem we were talking about. If you use original units, then basically your classifier is pretty much, the nearest neighbor classifier is pretty much only looking at the white blood cell count and is ignoring the other 2 attributes. It's not using all the information available to make a diagnosis. A doctor who only has 1 lab test result is probably gonna be less accurate, less able to make accurate diagnoses than one who has all 3 lab test results. That's huge, yeah. So depending on the data set, this can be a big problem. And so when using nearest neighbor classifier, it's often very helpful to convert to standard units so that they all have kind of the same range of variability. They all have standard deviation 1, and so are all kind of on a similar scale. Is there any instance where you shouldn't convert to standard units? There's no guarantees in anything in machine learning. In machine learning, anything could happen. It's possible the original units could be better, but typically converting to standard units won't hurt and may help a lot, as in this case. But there's no guarantees. You just have to try and see. So there's a lot of trial and error involved in doing machine learning work. Okay, so I've now introduced you to classifiers and machine learning. I want to give one cautionary remark about bias in machine learning, and you're going to hear more about this in after Thanksgiving break. Machine learning classifiers will pick up any bias that's present in your data set. It's easy to think that algorithms will avoid human bias, but let me tell you a story of a machine learning classifier that tried to look at Yelp restaurant reviews and determine how enthusiastic people were about the food they got there. For some reason, this machine learning classifier kept classifying Mexican restaurants as really, really bad, all of them as really bad, even though the reviews would say stuff like, this was great, I loved my dinner there, the Mexican food was awesome, I'm so glad I went to this Mexican restaurant. Turns out this machine learning classifier had learned how to understand what words mean by gathering data from the internet, and was trying to classify each word as this is positive or this is negative. And because it had collected data from the internet, and because there's a lot of racist stuff on the internet that was saying that associating Mexicans with bad immigrants and so on, the classifier had learned that Mexican was a negative word, had negative associations. And so every time you use the word Mexican in a review, it thought that you were saying that this restaurant was terrible. So this classifier had picked up human bias. So the algorithms are not any better than we are, and they sometimes can be a lot worse than they are. So you have to be very cautious about the risks of using this inscrutable machine learning technology that may be making decisions in ways that we would be completely uncomfortable with. And we'll learn more about that after Thanksgiving. All right, have a great weekend, and we will have lecture on Monday.